Please subscribe to support the channel. Imagine standing beneath a night sky scattered with stars, each one a distant sun burning across the vastness of space. Now imagine that everything you can see, every star, every galaxy, every cosmic structure scattered across the heavens, exists within a bubble of space that measures 93 billion light-years from one edge to the other. This is our observable universe, the totality of everything we could possibly see if we had perfect instruments and infinite time. But here's where things become genuinely puzzling, almost impossibly strange when you first encounter it. The universe is only 13.8 billion years old. Take a moment to let that sink in. If the universe began 13.8 billion years ago, and nothing can travel faster than light, shouldn't we only be able to see objects that are 13.8 billion light-years away at most? How can we possibly observe a universe that spans 93 billion light-years? The answer lies not in anything traveling faster than light, but in the fundamental nature of space itself. Space isn't just an empty stage where cosmic events unfold. Space is dynamic, malleable, and most importantly for our purposes, it's expanding. This is an expansion into anything, which is a common misconception. Space itself is stretching, carrying galaxies along with it like raisins in rising bread dough. When we look at distant galaxies, we see them as they were billions of years ago, when they emitted the light we're now receiving. But in the time it took that light to reach us, space has been expanding. The galaxy that emitted the light we see today has been carried much farther away by this expansion. When cosmologists calculate how far away that galaxy is now, accounting for all the expansion that has occurred in the intervening billions of years, they arrive at distances far greater than the age of the universe and light years would suggest. This expansion has been happening since the very beginning, since the moment of the Big Bang itself. In that first infinitesimal fraction of a second, space emerged and began expanding, and it has continued expanding ever since. The universe was hot, dense, filled with energy and fundamental particles. As it expanded, it cooled, allowing matter to form and eventually clump together under gravity to create the structures we see today. But the expansion never stopped. Every galaxy beyond our local group is moving away from us, and the farther away a galaxy is, the faster it appears to be receding. This relationship between distance and recession velocity was discovered by Edwin Hubble in the 1920s and remains one of the foundational observations of modern cosmology. The universe is not static. It's growing larger with every passing moment. Now, if we could somehow rewind cosmic history, running the expansion backward, we would see the universe becoming smaller, denser, and hotter as we approach the moment of the Big Bang. But we can't actually see all the way back to that initial moment. There's a limit to how far back in time we can observe, and it has to do with the nature of light and matter in the early universe. For the first 380,000 years after the Big Bang, the universe was so hot and dense that atoms couldn't form. Electrons were stripped from atomic nuclei, creating a plasma of charged particles. Light couldn't travel freely through this plasma because photons were constantly scattering off free electrons. The universe was opaque, like being inside a dense fog where light can't penetrate more than a short distance. But as the universe expanded and cooled, it eventually reached a temperature where electrons could combine with protons to form neutral hydrogen atoms. This event, called recombination, changed everything. Suddenly, light could travel freely through space without constantly scattering off charged particles. The universe became transparent. The photons that were released at that moment have been traveling through space ever since, and we can still detect them today. This is the cosmic microwave background radiation, one of the most important discoveries in the history of cosmology. It was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, who were trying to eliminate mysterious noise from a radio antenna. They discovered that this noise came from every direction in the sky equally, and couldn't be eliminated. What they had found was the afterglow of the Big Bang itself. The cosmic microwave background, often abbreviated as CMB, provides us with a snapshot of the universe as it appeared when it was just 380,000 years old. At that time, the temperature had dropped to about 3,000 degrees Kelvin, cool enough for atoms to form. The photons released during recombination have been traveling through space for more than 13 billion years, and because the universe has expanded so much during that time, these photons have been stretched to much longer wavelengths. What was once visible light is now microwave radiation, with a temperature of just 2.7 degrees above absolute zero. This faint radio signal permeates all of space, coming from every direction equally. It's everywhere, filling the universe, a cosmic fossil from the earliest epoch we can directly observe. When scientists study the CMB in detail, they find that it's not perfectly uniform. There are tiny variations in temperature, differences of only a few parts per 100,000, but these variations are incredibly important. They represent tiny density fluctuations in the early universe, regions that were slightly denser or slightly less dense than average. These variations were the seeds that would eventually grow into galaxies, galaxy clusters, and all the large-scale structures we see in the universe today. By studying the pattern of these fluctuations, cosmologists can learn about the composition of the universe, its age, its geometry, and the processes that occurred in its first moments. Satellites like COBE, WMAP, and Planck have mapped the CMB with ever-increasing precision, and each new measurement has refined our understanding of cosmic history. But when scientists analyze the CMB and study the motions of galaxies and galaxy clusters, they consistently find something unexpected. The matter we can see, all the stars, planets, gas clouds, and everything made of atoms, isn't enough to account for the gravitational effects we observe. When astronomers measure how fast stars orbit within galaxies, they find that the outer stars are moving much faster than they should if only visible matter were present. According to Newton's laws, stars farther from a galaxy's center should orbit more slowly, just as planets farther from the Sun orbit more slowly. But that's not what we observe. Stars at the edges of galaxies orbit just as fast or even faster than stars closer to the center, suggesting there's much more mass present than we can see. This discrepancy appears at every scale. Individual galaxies rotate too fast. Galaxy clusters contain more mass than can be accounted for by all their visible galaxies. When we observe the way galaxy clusters bend light from more distant objects behind them, a phenomenon called gravitational lensing, we find that they must contain far more mass than we can detect with any telescope, regardless of what wavelength we use. All of this evidence points to the existence of dark matter, an invisible form of matter that doesn't emit, absorb, or reflect light. We can't see it directly, but we can detect its presence through its gravitational effects on visible matter and light. Dark matter makes up approximately 27% of the universe's total mass energy content. That's more than 5 times as much as all the ordinary matter in the universe. Every atom in your body, every star in the sky, every planet and gas cloud, all of that comprises only about 5% of what exists. The rest is dark matter, and something even stranger that we'll discuss shortly. Scientists don't yet know what dark matter is made of. It's not made of atoms like ordinary matter. It doesn't interact with light, or with normal matter except through gravity. Various candidates have been proposed, from weakly interacting massive particles called WIMPs to axions to primordial black holes formed in the early universe. Experiments deep underground and in space are searching for direct evidence of dark matter particles, hoping to finally identify this mysterious substance that plays such a crucial role in cosmic structure. Without dark matter, galaxies as we know them couldn't exist. The gravity from visible matter alone isn't strong enough to hold them together given how fast they rotate. Without the additional gravity from dark matter, stars would fly apart, and galaxies would disintegrate. On larger scales, dark matter forms an invisible scaffolding throughout the universe. It clumps together under its own gravity, forming vast halos around galaxies and web-like filaments connecting galaxy clusters. Ordinary matter follows the gravitational pull of this dark matter scaffolding, flowing into the densest regions where it forms stars and galaxies. Computer simulations of cosmic structure formation only produce realistic results when they include dark matter. Without it, the universe would look completely different from what we observe. Yet as mysterious as dark matter is, it's not even the strangest component of our universe. In the late 1990s, 2 independent teams of astronomers were studying distant supernovae, trying to measure how much the universe's expansion had slowed down over cosmic history. Everyone expected to find that expansion was gradually slowing due to the mutual gravitational attraction of all matter in the universe. The only question was whether there was enough matter to eventually halt the expansion and cause the universe to collapse, or whether expansion would continue forever but gradually slow down. What these teams discovered shocked the scientific community. The expansion of the universe isn't slowing down at all. It's accelerating. This was completely unexpected. Acceleration requires energy, some form of repulsive force pushing space apart faster and faster. Scientists named this mysterious phenomenon dark energy, though that name tells us little about what it actually is. Dark energy comprises roughly 68% of everything that exists in the universe. It's the dominant component, making up more than twice as much as dark matter and more than 13 times as much as ordinary matter. Yet we have no idea what it is. We can measure its effects with great precision, observing how it causes distant galaxies to accelerate away from us, but its fundamental nature remains one of the greatest unsolved mysteries in physics. Several theories attempt to explain dark energy. One possibility is that it represents the energy of empty space itself, what physicists call vacuum energy. According to quantum field theory, even completely empty space isn't truly empty but seethes with quantum fluctuations, particles and antiparticles constantly appearing and disappearing. These fluctuations should contribute energy to space, and this energy would act like dark energy, causing cosmic acceleration. The problem is that when physicists calculate how much vacuum energy there should be, they get an answer that's larger than the observed amount of dark energy by a factor of 10 to the 120th power. This is arguably the worst prediction in the history of physics, an error so large it suggests something fundamental about our theories is wrong. Another possibility is that dark energy isn't constant but varies over time or space. Some theories propose new fields permeating space, analogous to the electromagnetic field but with different properties. Others suggest that our understanding of gravity itself may need modification on cosmic scales. Perhaps Einstein's general relativity, which has passed every test on solar system scales, needs adjustment when applied to the entire universe. These ideas remain speculative, and distinguishing between them requires extremely precise measurements of cosmic expansion at different epochs. Current and future surveys are mapping the distribution and motion of galaxies across the observable universe, hoping to find clues that will reveal the nature of dark energy. What we do know is that dark energy is causing the universe to expand at an accelerating rate, and this has profound implications for the future of the cosmos. But before we explore those implications, let's ground ourselves in the structures we can actually see, the galaxies that populate space and give the universe its visible face. Our home galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars. The uncertainty in that number reflects how difficult it is to count stars in our own galaxy. We're embedded within it, and dust clouds block our view in many directions, particularly toward the galactic center. But even taking the lower estimate, 100 billion stars is a number almost impossible to grasp intuitively. If you tried to count every star in the Milky Way, counting one per second without stopping, it would take you more than 3,000 years. Each of those stars is a massive ball of plasma, fusing hydrogen into helium in its core and releasing enormous amounts of energy. Some stars are smaller and cooler than our Sun, dim red dwarfs that can burn for trillions of years. Others are massive blue giants that burn through their fuel in just a few million years. There are binary star systems where two stars orbit each other, triple systems, even systems with 6 or 7 stars bound together by gravity. Around many of these stars orbit planets, worlds as diverse as the stars themselves. Some are gas giants larger than Jupiter, others are rocky worlds like Earth, still others are strange water worlds or planets with exotic atmospheres nothing like anything in our solar system. The Milky Way itself is just one galaxy among countless billions in the observable universe. Estimates suggest there are somewhere between 200 billion and 2 trillion galaxies within the volume of space we can observe. Each one contains millions, billions, or even trillions of stars. They come in various shapes and sizes. Spiral galaxies like the Milky Way have elegant arms winding outward from a central bulge, regions where new stars are actively forming from clouds of gas and dust. Elliptical galaxies are roughly spherical or football-shaped, containing mostly older stars and little gas for new star formation. Irregular galaxies have no particular shape, their structure disrupted by gravitational interactions with neighbors. Then there are dwarf galaxies containing only millions of stars, gravitationally bound to larger galaxies as satellites. All of these galaxies are scattered through space at vast distances from one another. To make sense of cosmic distances, astronomers use units called light years. 1 light year is the distance light travels in 1 year, moving at its constant speed of about 300,000 kilometers per second. That works out to roughly 9.5 trillion kilometers or 6 trillion miles. It's a vast distance, almost incomprehensible on human scales. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away. The center of our galaxy is roughly 26,000 light-years distant. The Andromeda Galaxy, our nearest large galactic neighbor, lies about 2.5 million light-years away. This brings us to one of the most profound aspects of astronomy. When we look at distant objects in space, we're not seeing them as they are now. We're seeing them as they were when the light we're receiving left them. When you look at the Sun, you see it as it appeared 8 minutes ago because that's how long it takes light to travel from the Sun to Earth. When you see Proxima Centauri, you see it as it was 4.2 years ago. When we observe the Andromeda Galaxy, we see it as it appeared 2.5 million years ago, long before modern humans existed. Looking deeper into space means looking further back in time. Those most distant galaxies we can observe, their light has been traveling toward us for more than 13 billion years. We see them as they were when the universe was young, in some cases less than 1 billion years after the Big Bang. This means we can actually observe cosmic history unfolding. By comparing nearby galaxies to distant ones, we see how galaxies have evolved over billions of years. Distant galaxies appear smaller, more irregular, more actively forming stars. Nearby galaxies are larger, more structured, and contain older stellar populations. The universe has changed dramatically over cosmic time, and we can trace those changes by looking at objects at different distances. This is one of the most powerful tools available to cosmologists. We can't watch individual galaxies evolve because the timescales are too long, but we can observe many galaxies at different stages of evolution and piece together the overall story. At the heart of nearly every large galaxy, including our own Milky Way, lurks something extraordinary and terrifying, a supermassive black hole. These objects contain millions or even billions of times the mass of our Sun, all compressed into a region smaller than our solar system. The supermassive black hole at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million suns. That might sound like a lot, but it's actually relatively modest compared to some other galaxies. The black hole at the center of the giant elliptical galaxy M87, which made headlines when it became the first black hole ever directly imaged, has a mass of about 6.5 billion suns. Even more massive examples have been discovered, some exceeding 10 billion solar masses. These supermassive black holes play a crucial role in galaxy formation and evolution. As matter falls toward them, it forms a swirling accretion disk, heating up to tremendous temperatures through friction. This heated matter emits enormous amounts of radiation before crossing the event horizon and disappearing forever. The energy released by matter falling into supermassive black holes can outshine the entire galaxy of stars surrounding them. This radiation can blow gas and dust out of the galaxy, shutting down star formation and affecting how the galaxy evolves. The relationship between supermassive black holes and their host galaxies is complex and still not fully understood, but observations show that the mass of the central black hole is tightly correlated with properties of the surrounding galaxy, suggesting they grow and evolve together. How supermassive black holes form in the first place remains an active area of research. They could grow from stellar mass black holes that form when massive stars die, gradually accumulating matter over billions of years. Or they might form more directly in the early universe from the collapse of enormous clouds of gas. Or perhaps they grow from the merger of many smaller black holes as galaxies collide and merge. Probably all these processes contribute to some degree. What's clear is that supermassive black holes were present very early in cosmic history. We observe bright quasars powered by supermassive black holes in galaxies less than 1 billion years after the Big Bang, suggesting these monsters formed remarkably quickly on cosmic timescales. Speaking of stars, their life cycles are among the most fundamental processes in the universe. Stars are born in giant clouds of gas and dust called nebulae. These clouds are mostly hydrogen and helium left over from the Big Bang, mixed with heavier elements forged in previous generations of stars. When a region of a nebula becomes dense enough, gravity begins to pull it inward. As the cloud contracts, it heats up. Eventually the core becomes so hot and dense that hydrogen nuclei begin fusing together to form helium. Nuclear fusion releases enormous energy, creating an outward pressure that balances gravity's inward pull. A star is born. The mass of a star determines everything about its life and death. Small stars, red dwarfs with less than half the sun's mass, burn their fuel so slowly they can shine for trillions of years, longer than the current age of the universe. These stars are so dim you need a telescope to see them, but they're actually the most common type of star in the galaxy. Medium-sized stars like our Sun have lifetimes measured in billions of years. Our Sun is about halfway through its life right now, having shone for approximately 4.5 billion years with another 5 billion or so to go. Massive stars, those with more than 8 times the Sun's mass, burn hot and bright but exhaust their fuel in mere millions of years. When a star like our Sun exhausts the hydrogen in its core, fusion stops and the core contracts under gravity, heating up. This causes the outer layers to expand enormously, and the star becomes a red giant, swelling to hundreds of times its original size. When the Sun reaches this stage, it will likely engulf Mercury, Venus, and possibly Earth. In the core, temperatures rise high enough to fuse helium into carbon and oxygen. Eventually, the star sheds its outer layers into space, creating a beautiful planetary nebula, while the core remains as a white dwarf. A white dwarf is incredibly dense, with about the mass of the Sun compressed into something roughly the size of Earth. It no longer undergoes fusion but shines by radiating away its stored heat. White dwarfs will slowly cool over trillions of years, eventually becoming cold black dwarfs, though the universe isn't old enough yet for any black dwarfs to have formed. Massive stars have far more dramatic endings. After exhausting hydrogen in their cores, they fuse helium into carbon and oxygen, then carbon into neon and magnesium, then neon into oxygen and magnesium, then oxygen into silicon and sulfur, and finally silicon into iron. Each stage burns faster than the last. A massive star might spend millions of years fusing hydrogen, but only days fusing silicon. The problem is that iron fusion doesn't release energy. It requires energy input. So once an iron core builds up, fusion stops. With no outward pressure from fusion to balance gravity, the core collapses catastrophically in less than a second. Electrons are forced into protons, creating neutrons and releasing neutrinos. The core becomes so dense that it rebounds, sending a shockwave outward that tears the star apart in a supernova explosion. For a few weeks, a supernova can outshine an entire galaxy. The explosion scatters heavy elements into space, enriching the interstellar medium with carbon, oxygen, silicon, iron, and all the other elements necessary for planets and life. The supernova shockwave can also compress nearby gas clouds, triggering new star formation. In this way, stars seed the cosmos with the raw materials for future generations of stars and planets. The Sun and Earth formed from gas enriched by countless previous generations of stars. Every atom in your body heavier than hydrogen was forged in a star or a supernova. We are, quite literally, made of stardust. What remains after a supernova depends on the mass of the collapsing core. If the core has between about 1.4 and 3 solar masses, it becomes a neutron star. Neutron stars are some of the most extreme objects in the universe. They pack more mass than the Sun into a sphere only about 20 kilometers across, roughly the size of a city. The density is so extreme that atomic nuclei are crushed together, and matter exists as a sea of neutrons. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The gravitational field at the surface is hundreds of billions of times stronger than Earth's. If you somehow stood on a neutron star, you would be instantly crushed into a layer of atoms less than a nanometer thick. Many neutron stars spin rapidly, completing dozens or even hundreds of rotations per second. This rapid rotation is a consequence of conservation of angular momentum. When the core of a star collapses, whatever rotation it had speeds up dramatically, like a figure skater pulling in their arms to spin faster. If the neutron star has a strong magnetic field aligned with its rotation axis, it emits beams of radiation from its magnetic poles. As the star spins, these beams sweep across space like lighthouse beams. If one happens to point toward Earth, we detect a regular pulse of radiation, and we call the object a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, who initially wondered if the incredibly regular pulses might be artificial signals from an alien civilization. Pulsars are now recognized as some of the most precise clocks in the universe, with some maintaining their pulse rate to nanosecond precision. If the collapsing core is more massive than about 3 solar masses, even the pressure from neutrons can't resist gravity. The collapse continues until the core becomes a black hole. Nothing, not even light, can escape from inside a black hole's event horizon. The mathematics of general relativity predict that all the mass collapses to an infinitely dense point called a singularity, though many physicists suspect quantum effects not included in general relativity would prevent true infinities from forming. Regardless of what happens at the very center, the region around a black hole is profoundly strange. Time itself slows down near the event horizon, and from the perspective of a distant observer, anything falling toward a black hole appears to slow down and freeze at the horizon, taking infinite time to cross it. From the perspective of the infalling object, however, the crossing happens in finite time, though extreme tidal forces would stretch and compress anything approaching the singularity in a process colorfully termed spaghettification. While black holes and neutron stars represent the exotic endpoints of stellar evolution, planets orbiting ordinary stars have become one of the most exciting areas of astronomical research in recent decades. For most of human history, we could only speculate about whether planets existed around other stars. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995, when Michel Mayor and Didier Queloz discovered a planet orbiting the star 51 Pegasi. Since then, thousands of exoplanets have been discovered, with the count now exceeding 5,000 confirmed worlds and thousands more candidates awaiting confirmation. These discoveries have revealed that planets are extraordinarily common. Current estimates suggest there are more planets than stars in our galaxy. Most stars appear to host at least one planet, and many have multiple planets in complex orbital architectures. The diversity of these worlds is staggering. We've found hot Jupiters, gas giants that orbit extremely close to their stars with surface temperatures hot enough to melt iron. We've found super-Earths, rocky worlds more massive than Earth but smaller than Neptune, a type of planet that doesn't exist in our solar system. We've found water worlds, planets where the entire surface may be covered by a deep ocean. We've found planets orbiting binary stars, systems where two stars orbit each other while planets orbit around both. We've even found rogue planets, worlds ejected from their stellar systems and wandering alone through interstellar space. Astronomers use several methods to detect exoplanets. The most successful has been the transit method, which looks for tiny dips in a star's brightness when a planet passes in front of it from our perspective. By measuring how much the star dims and how long the transit lasts, astronomers can determine the planet's size and orbital period. The Kepler Space Telescope used this method to discover thousands of planets. Another important technique is the radial velocity method, which detects the subtle wobble in a star's motion caused by an orbiting planet's gravity. Massive planets close to their stars cause the largest wobbles and were the first to be discovered, which is why many early exoplanet discoveries were hot Jupiters. As techniques have improved, astronomers have been able to detect smaller planets at greater distances from their stars, including some in the habitable zone. The discovery of so many planets naturally leads to questions about life beyond Earth. Are we alone in the universe, or is life common wherever conditions permit? Nobody yet knows the answer, but we can at least identify the conditions necessary for life as we know it. Life requires liquid water, organic molecules, and an energy source. On Earth, all known life is based on carbon chemistry and requires water as a solvent. While it's possible to imagine forms of life based on different chemistry, we have no examples to study, so the search for life focuses on finding conditions similar to those on Earth. This leads to the concept of the habitable zone, sometimes called the Goldilocks zone, the range of distances from a star where a planet's surface temperature could allow liquid water to exist. Too close to the star and water boils away. Too far and it freezes solid. The habitable zone's location and width depend on the star's temperature and brightness. Around hot, bright stars, the habitable zone is far from the star and quite wide. Around cool, dim red dwarfs, it's close to the star and narrow. Our solar system's habitable zone extends roughly from Venus's orbit to Mars's orbit, with Earth comfortably in the middle. Both Venus and Mars likely had liquid water on their surfaces in the distant past, though Venus underwent a runaway greenhouse effect and Mars lost most of its atmosphere, so neither is habitable today. Finding a planet in the habitable zone doesn't guarantee it's habitable. Many other factors matter. The planet needs to be rocky with a solid surface, not a gas giant. It needs an atmosphere with the right composition and pressure. Too thick an atmosphere and you get a runaway greenhouse like Venus. Too thin and water can't remain liquid. The planet probably needs a magnetic field to shield its surface from harmful cosmic radiation and prevent the solar wind from stripping away its atmosphere. It likely needs plate tectonics to recycle carbon and regulate the climate over geological timescales. The star needs to be stable and not prone to violent flares that would sterilize the planet's surface. The planet's orbit should be reasonably circular so its distance from the star doesn't vary too much. It probably helps to have a large moon to stabilize the planet's rotation axis and prevent wild climate swings. When you add up all these requirements, habitable planets might be fairly rare, or they might be common. We simply don't know yet because we're only beginning to study exoplanet atmospheres and characteristics in detail. Several potentially habitable planets have been discovered orbiting nearby stars. Proxima Centauri b, the closest known exoplanet, orbits in its star's habitable zone, though Proxima Centauri is a red dwarf prone to intense flares that might make life difficult. The TRAPPIST-1 system contains 7 Earth-sized planets, 3 of which orbit in the habitable zone, all packed into orbits closer to their star than Mercury is to our Sun. These are tantalizing targets for future study with next-generation telescopes that will be able to analyze their atmospheres looking for biosignatures, chemical signatures of life like oxygen and methane present together in ways that non-biological processes can't easily explain. The question of life's prevalence connects to deeper questions about cosmic origins and the early universe. To understand how we got from the Big Bang to a universe filled with galaxies, stars, and planets, we need to understand what happened in the first moments after the universe began. According to the standard Big Bang model, the universe emerged from an initial singularity 13.8 billion years ago, and has been expanding ever since. But that simple description leaves many questions unanswered. Why is the universe so uniform on large scales? The CMB has almost exactly the same temperature in all directions, implying that widely separated regions of the early universe had time to come into equilibrium. But if we calculate how far light could have traveled in the first 380,000 years, we find that most of the regions we see in the CMB should never have been in contact with each other. They couldn't have exchanged light or matter or information, so why do they all have the same temperature? Another puzzle is the flatness problem. Measurements show that the universe's geometry is flat or extremely close to flat, meaning the density of matter and energy is almost exactly equal to the critical density that marks the boundary between a universe that will eventually collapse and one that will expand forever. But this critical density is an unstable equilibrium point. Any tiny deviation from flatness in the early universe would have been amplified by expansion, and by now the universe should be dramatically curved one way or the other. The fact that it's still flat after 13.8 billion years of expansion suggests the early universe must have been flat to extraordinary precision, which seems like an unlikely coincidence. The solution to these and other problems is cosmic inflation, a theory proposing that the universe underwent a brief period of exponential expansion in its first fraction of a second. During inflation, the universe doubled in size many times over in an incredibly short period, perhaps increasing in volume by a factor of 10 to the power of 78, or more in just 10 to the negative 34 seconds. This rapid expansion stretches out any curvature, making the universe appear flat, just as the surface of a balloon appears flat if you inflate it to an enormous size. It also explains the uniformity of the CMB because regions that appear widely separated today were actually very close together before inflation began, close enough to reach thermal equilibrium. Inflation also provides a mechanism for creating the tiny density fluctuations we see in the CMB. According to quantum mechanics, even empty space experiences fluctuations at microscopic scales. During inflation, these quantum fluctuations were stretched to enormous sizes, becoming density variations across the universe. These variations were tiny, just a few parts per 100,000, but they were enough to seed the formation of all cosmic structure. Regions that were slightly denser had slightly stronger gravity, attracting more matter, becoming even denser, eventually collapsing to form the first stars and galaxies. The pattern of galaxies we see in the universe today traces back to quantum fluctuations from the inflationary epoch. While inflation solves several cosmological puzzles and makes predictions that match observations, the mechanism that drove it remains uncertain. Most inflation models propose a hypothetical field called the inflaton field that filled space in the early universe. This field had potential energy, and as it slowly rolled down its potential, that energy drove exponential expansion. Eventually the field reached the bottom of its potential and inflation ended, with the field's energy converting into ordinary matter and radiation, reheating the universe. This transition from inflation to the normal expansion phase is called reheating, and it marks the beginning of the hot Big Bang phase that led to nucleosynthesis, recombination, and eventually structure formation. Different inflation models make slightly different predictions about the statistical properties of CMB fluctuations and the production of gravitational waves during inflation. Observations have confirmed many of inflation's predictions while ruling out some specific models. Future observations may be able to detect primordial gravitational waves from inflation, which would provide strong evidence for the theory and constrain what kind of inflaton field drove it. For now, inflation remains the leading explanation for the large-scale properties of the universe, though alternatives continue to be explored. Looking forward into the deep future, what will happen to the universe? Will expansion continue forever? Will it slow and reverse? Or will something else occur? The answer depends on the universe's composition and the nature of dark energy. Before dark energy was discovered, cosmologists considered three possibilities. If the universe's density was above the critical value, gravity would eventually overcome expansion, pulling everything back together in a big crunch, a reverse of the Big Bang. If the density was below critical, expansion would continue forever, gradually slowing but never stopping, ending in a big freeze as stars burn out and galaxies drift apart. If the density was exactly critical, the universe would expand forever but at an ever-decreasing rate, asymptotically approaching zero. The discovery that expansion is accelerating changes this picture dramatically. If dark energy behaves like Einstein's cosmological constant, remaining constant over time, then the universe will continue accelerating indefinitely. Distant galaxies will recede faster and faster until they're moving away so quickly their light can never reach us. Over hundreds of billions of years, all galaxies beyond our local cluster will disappear beyond a cosmic horizon. The sky will become darker and emptier. Eventually, only the local group of gravitationally bound galaxies will remain visible, with everything else having receded beyond reach. Stars will continue forming for a while from remaining gas, but eventually all the gas will be consumed or dispersed. Stellar lifetimes will run their course. The longest-lived red dwarfs will burn for trillions of years, but they too will eventually exhaust their fuel. The universe will be populated only by dead remnants, white dwarfs, neutron stars, and black holes, drifting through an expanding void. Even these remnants won't last forever. On timescales so long they're hard to comprehend, white dwarfs and neutron stars will likely decay, their constituent protons breaking down if certain theories of particle physics are correct. Black holes will evaporate through Hawking radiation, a quantum mechanical process that causes them to emit particles and very slowly lose mass. A stellar mass black hole would take 10 to the 67 years to evaporate. A supermassive black hole like the one at the Milky Way's center would take 10 to the 100 years. These timescales are so immense that the current age of the universe, 13.8 billion years or about 10 to the 10 years, is utterly insignificant by comparison. Eventually, perhaps 10 to the 100 years in the future or even longer, all black holes will evaporate, leaving a universe of isolated photons and fundamental particles in an ever-expanding, cooling void. This is the Big Freeze, the most likely fate of our universe given current observations. However, if dark energy isn't constant but instead increases over time, a more dramatic fate is possible. In this scenario, called the Big Rip, dark energy grows stronger and stronger, eventually overcoming not just gravity but all fundamental forces. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then eventually atoms themselves as dark energy rips apart even the electromagnetic forces binding electrons to nuclei. The Big Rip would occur at some finite time in the future, perhaps tens of billions of years from now, ending with all matter and space disintegrating. Current observations suggest this isn't the likely fate. Dark energy appears to be consistent with a cosmological constant, but we can't yet rule out more exotic possibilities with absolute certainty. There are other speculative scenarios as well. Some theories suggest the universe could undergo a phase transition, similar to how water suddenly freezes when cooled below 0 degrees Celsius. If the vacuum of space isn't in its lowest energy state, it could suddenly transition to a lower state, releasing enormous energy and fundamentally changing the laws of physics throughout the universe. This is called vacuum decay, and if it occurs, a bubble of new vacuum would expand at the speed of light, obliterating everything it encounters and replacing it with matter governed by different physical laws. We would have no warning because the bubble would arrive at the speed of light. One moment the universe would exist as we know it, and the next moment everything would be transformed. The fact that this hasn't happened yet suggests either that our vacuum is stable, or that we've been lucky so far. All these future scenarios involve timescales so vast they're essentially meaningless from any human perspective. The Sun will exhaust its hydrogen in about 5 billion years, long before any of these cosmic endings come to pass. Life on Earth faces more immediate concerns from the gradually brightening Sun, which will render Earth uninhabitable in perhaps 1 billion years as increased solar radiation boils away the oceans. Human civilization, if it survives and flourishes, will need to spread beyond Earth long before then. Perhaps our descendants will inhabit other star systems throughout the galaxy, or even other galaxies, before the universe's ultimate fate becomes relevant. Or perhaps intelligence will find ways to persist even in the far future, extracting energy from black hole evaporation or finding other means to continue thinking and existing even as the cosmos grows cold and dark. But let's return from these distant futures to phenomena we can observe today. Among the most luminous objects in the universe are quasars, which appear as star-like points of light but are actually extraordinarily distant and bright. When quasars were first discovered in the 1960s, their nature was completely mysterious. They looked like stars but had strange spectra that didn't match any known object. Eventually, astronomers realized that quasars are the extremely bright cores of distant galaxies, powered by supermassive black holes actively consuming vast amounts of matter. The term quasar is short for quasi-stellar radio source, because many were first detected as bright radio sources that look like stars when viewed in visible light. A quasar occurs when matter falls into a supermassive black hole at an extremely high rate, forming a bright accretion disk that can outshine the entire galaxy of stars surrounding it by a factor of 100 or 1,000. The intense radiation from the accretion disk heats surrounding gas, causing it to glow. Jets of particles moving at nearly the speed of light can be launched perpendicular to the accretion disk, extending for hundreds of thousands of light years into space. These jets emit powerful radio waves and other radiation. Quasars are so bright that we can see them across most of the observable universe. The most distant quasars we've detected existed when the universe was less than 1 billion years old, their light traveling for more than 13 billion years to reach us. The fact that quasars exist so early in cosmic history tells us something important. Supermassive black holes formed remarkably quickly after the Big Bang. How they grew to billions of solar masses so rapidly remains an active research question. It also tells us that the early universe was a more violent, energetic place than the universe today. When we survey the sky, we find many quasars at high redshifts, meaning great distances and early cosmic times, but very few quasars nearby. This implies that quasars were much more common billions of years ago than they are now. The universe has calmed down over time. In the early universe, galaxies had more gas available to fuel their central black holes, leading to frequent quasar activity. As galaxies evolved and gas was consumed by star formation or blown away by supernova explosions and quasar radiation, fewer galaxies had enough fuel to power bright quasars. Our own Milky Way probably went through a quasar phase billions of years ago when it had more gas falling into its central black hole. Today, Sagittarius A star is relatively quiet, consuming matter at a much lower rate. But occasionally it flares up, brightening briefly as a clump of matter falls in. If we could observe the Milky Way from a distant galaxy, we would see it as a fairly normal spiral galaxy with no quasar at its center. This is typical of most nearby galaxies. The quasar era has mostly passed, at least for now. Future galaxy mergers could reignite quasar activity by channeling fresh gas towards central black holes, but such events will become increasingly rare as cosmic expansion carries galaxies farther apart. The search for habitable planets and potential life connects to questions about what conditions are necessary for life to emerge and persist. On Earth, life appears to have emerged quite quickly once conditions became favorable, within the first billion years after the planet formed. This might suggest life arises readily wherever conditions permit, or it might mean we were lucky. We have only one example to study, which makes generalizing impossible. Life on Earth has persisted for nearly 4 billion years despite numerous catastrophes, including asteroid impacts, volcanic eruptions, ice ages, and mass extinctions. The resilience of life once established is remarkable. Extremophile organisms live in boiling hot springs, frozen Antarctic ice, deep ocean trenches, intensely acidic waters, and even inside nuclear reactor cooling pools. This resilience suggests that once life gets started, it can adapt to a wide range of conditions. But getting started may be the hard part. We don't fully understand how life first emerged from non-living chemistry. Laboratory experiments have shown that organic molecules, including amino acids, can form spontaneously under conditions thought to resemble the early Earth. But going from simple organic molecules to self-replicating life involves crossing a threshold we haven't yet been able to replicate in the lab. Some scientists think life emerged in warm ponds on land, where cycles of wetting and drying could concentrate organic molecules and promote the formation of complex structures. Others favor deep-sea hydrothermal vents, where chemical energy from geological processes could drive the reactions necessary for life. Still others speculate that life might have originated in space, forming on comets or asteroids and being delivered to Earth through impacts, though this just pushes the question back to where and how life formed in the first place. If life is common in the universe, we might expect to see evidence of it, or at least evidence of intelligent civilizations that have developed technology. This is the basis of the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" If intelligent life is common, and if even a tiny fraction of civilizations develop interstellar travel, the galaxy should have been colonized many times over by now given its age. Yet we see no evidence of extraterrestrial civilizations. This could mean intelligent life is extraordinarily rare, perhaps unique to Earth. Or it could mean civilizations tend to destroy themselves before achieving interstellar travel. Or perhaps interstellar travel is simply too difficult and expensive to be practical, even for advanced civilizations. Or maybe advanced civilizations deliberately avoid contact with primitive ones like us. Or perhaps we're looking in the wrong ways or at the wrong wavelengths. The answer could profoundly affect our understanding of our place in the cosmos. One of the most revolutionary developments in astronomy came in 2015 with the first direct detection of gravitational waves. Predicted by Einstein's general theory of relativity a century earlier, gravitational waves are ripples in the fabric of spacetime itself, caused by the acceleration of massive objects. Einstein showed that gravity isn't a force in the traditional sense but rather a consequence of massive objects curving the geometry of spacetime. When massive objects accelerate, they create disturbances that propagate outward at the speed of light as gravitational waves. These waves alternately stretch and compress space itself as they pass through. For decades, detecting gravitational waves seemed impossible because the effects are incredibly tiny. Even the most violent cosmic events produce waves that change distances by less than 1 part in 10 to the 21st. That means detecting them requires measuring length changes smaller than 1,000th the diameter of a proton across distances of several kilometers. The Laser Interferometer Gravitational Wave Observatory, LIGO, achieved this impossible-seeming measurement using laser interferometry at 2 facilities separated by thousands of kilometers. On September 14, 2015, both detectors simultaneously registered a gravitational wave signal lasting less than a second. Analysis showed the signal came from 2 black holes, each about 30 times the Sun's mass, spiraling together and merging about 1.3 billion light-years away. This detection opened a new window on the universe. For all of human history, our understanding of the cosmos came from electromagnetic radiation, visible light, radio waves, X-rays, and so on. Now we can observe the universe through an entirely different medium, detecting events that produce little or no light. Since that first detection, dozens of gravitational wave events have been observed, mostly from merging black holes but also from merging neutron stars. The neutron-star merger detected in 2017 was especially important because it was observed with both gravitational waves and electromagnetic radiation, allowing astronomers to study the event across multiple wavelengths. This merger likely produced heavy elements like gold and platinum through rapid neutron capture, confirming that neutron-star mergers are a major source of heavy elements in the universe. Future gravitational wave detectors will be even more sensitive, able to detect signals from farther away and from less massive objects. Space-based detectors like the planned Laser Interferometer Space Antenna, LISA, will be sensitive to lower-frequency gravitational waves from supermassive black hole mergers, opening yet another observational window. Gravitational wave astronomy is still in its infancy, but it has already transformed our understanding of black holes, neutron stars, and the violent processes that shape the cosmos. It provides a way to test general relativity in extreme conditions where spacetime is curved dramatically, and so far Einstein's century-old theory has passed every test. The large-scale structure of the universe is as remarkable as its smallest details. When astronomers map the distribution of galaxies across enormous volumes of space, they find that galaxies aren't distributed randomly. Instead, they trace out an enormous cosmic web, a network of filaments and sheets surrounding vast empty regions called cosmic voids. Galaxy clusters lie at the intersections of filaments, like cities at the junctions of highways. The filaments themselves are long chains of galaxies stretching for hundreds of millions of light-years. Between the filaments lie the voids, regions containing very few galaxies that can span 100 million light-years or more across. This cosmic web structure traces back to the tiny density variations present in the early universe. Regions that were slightly denser attracted more matter through gravity, becoming even denser over time. But the universe was also expanding, and in lower density regions, expansion won out over gravity. These regions became even emptier as matter flowed toward denser regions. Computer simulations of structure formation, starting from the initial conditions revealed by the CMB and including dark matter and dark energy, reproduce the cosmic web structure we observe. The simulations showed dark matter forming filaments first, with ordinary matter following the dark matter's gravitational pull. Within the densest regions, matter collapses to form galaxies and galaxy clusters. The largest cosmic void known is the Eridanus supervoid, spanning roughly 1 billion light-years across. Within such voids, galaxies are extremely rare, perhaps only a few percent as dense as in average regions of space. From a hypothetical planet in a void galaxy, the night sky would be much emptier than our own. You might see a few nearby galaxies, but the vast cosmic tapestry of billions of galaxies would be invisible, all lying beyond the void's far boundary. Intelligent beings evolving in such an environment might develop very different cosmologies than we have, perhaps believing their small group of galaxies was the entire universe. It's a reminder of how our cosmic perspective depends on our particular location. When cosmologists study the universe's geometry and evolution, they find strong evidence that space is flat or extremely close to flat on large scales. But what does it mean for space to be flat? In general relativity, space can have different geometries depending on its energy density. If the total density is above a critical value, space curves back on itself like the surface of a sphere. In such a closed universe, you could theoretically travel in a straight line and eventually return to your starting point, though the universe's finite age makes this impossible in practice. If the total density is below critical, space curves the opposite way, like a saddle. This is called an open universe. If the density equals the critical value exactly, space is flat, extending infinitely in all directions without curvature. Measurements of the CMB indicate the universe's total density is extremely close to critical, making space flat to within measurement error. This flatness connects to the universe's ultimate fate. A flat universe with dark energy that behaves like a cosmological constant will expand forever at an accelerating rate, leading to the big freeze scenario discussed earlier. The flatness is also one of the key predictions of inflation, which stretches out any initial curvature and drives the density toward the critical value. The fact that the universe remains flat after 13.8 billion years of expansion provides strong evidence that inflation occurred. However, there's an important distinction between the observable universe and the universe as a whole. When we say space is flat, we mean the portion we can observe is flat. But the universe likely extends far beyond what we can see. Light from regions more than about 46 billion light-years away hasn't had time to reach us yet, and because of accelerating expansion, light from even more distant regions never will. The observable universe is just a bubble within what might be a vastly larger cosmos. The universe as a whole could have some large-scale curvature that we can't detect because we only see a small patch of it, much like Earth's surface appears flat locally even though the planet is spherical. This raises profound questions about what lies beyond our cosmic horizon. Is the universe infinite, or does it have a finite size? If it's finite, does it have an edge, or does space wrap around on itself? These questions may be unanswerable, at least with current technology, because we can only observe the portion of space from which light has had time to reach us. Everything beyond our horizon is forever inaccessible, causally disconnected from us by the expansion of space. For all practical purposes, the observable universe is the only universe we can ever know anything about. One of the deepest mysteries in cosmology concerns why the universe contains matter rather than equal amounts of matter and antimatter. According to the known laws of physics, matter and antimatter should have been created in equal quantities in the Big Bang. Every particle has an antiparticle counterpart with the same mass but opposite charge. When a particle meets its antiparticle, they annihilate, converting their mass into energy according to Einstein's equation E equals mc squared. If matter and antimatter were created in equal amounts, they should have completely annihilated each other, leaving only radiation. Yet we exist, and we live in a universe made almost entirely of matter with very little antimatter. Somehow, the early universe must have produced slightly more matter than antimatter, perhaps one extra matter particle for every billion matter-antimatter pairs. When most particles and antiparticles annihilated, this tiny excess of matter remained. That residual matter is everything we see today: stars, planets, galaxies, and ourselves. But what created this asymmetry? The physics we understand predicts that processes creating matter should create equal amounts of antimatter. To generate a matter-antimatter imbalance requires three conditions, called the Sakharov conditions after physicist Andrei Sakharov, who identified them. First, there must be processes that violate baryon number conservation, allowing the number of matter particles to change. Second, these processes must treat matter and antimatter slightly differently, a property called charge parity violation. Third, these processes must occur out of thermal equilibrium, meaning the universe must be cooling or changing in some way. We know that charge parity violation occurs in the weak nuclear force, which governs certain types of radioactive decay. Laboratory experiments have detected small differences in how matter and antimatter behave under the weak force. However, the amount of violation observed isn't enough to explain the universe's matter-antimatter asymmetry. There must be additional sources of asymmetry beyond what we've detected so far. Many theories propose new physics beyond the standard model of particle physics that could generate sufficient asymmetry. Some involve heavy particles that existed only in the early universe, decaying asymmetrically to produce more matter than antimatter. Others involve complex interactions during phase transitions in the first moments after the Big Bang. Testing these theories is difficult because they involve energies far beyond what particle accelerators can reach, but cosmological observations and searches for extremely rare particle decays continue to constrain the possibilities. If this asymmetry hadn't occurred, if the universe contained equal matter and antimatter, those particles would have annihilated, leaving only photons and perhaps neutrinos. There would be no atoms, no chemistry, no stars, no planets, and certainly no life. The fact that we exist to ponder these questions tells us something important about cosmic history. The universe must have gone through processes that slightly favored matter over antimatter, allowing structure to form. Understanding exactly what those processes were remains one of the major unsolved problems in physics. Among the most extreme objects in the universe, even more extreme than ordinary neutron stars, are magnetars. These are neutron stars with magnetic fields roughly 1,000 trillion times stronger than Earth's. To put that in perspective, Earth's magnetic field is strong enough to deflect compass needles and protect us from solar wind. A magnetar's field is so intense that it would be lethal at a distance of 1,000 kilometers, tearing apart atoms by warping their electron clouds into cigar shapes. At a distance of 1 astronomical unit, about the Earth-Sun distance, a magnetar's magnetic field would erase every credit card on Earth and destroy electronic devices. The physics occurring near magnetars is unlike anything anywhere else in the observable universe. Quantum electrodynamics, the theory describing how light interacts with matter, predicts strange effects in extremely strong magnetic fields. Light behaves differently, and vacuum itself can become birefringent, splitting light into different polarizations traveling at different speeds. The space around a magnetar is filled with powerful X-rays and gamma rays emitted as the intense magnetic field decays and realigns. Sometimes magnetars undergo star quakes, where the solid crust of the neutron star suddenly cracks and shifts under magnetic stress, releasing enormous bursts of energy. One such flare from a magnetar 28,000 light-years away in 2004 briefly overwhelmed every X-ray detector in the solar system despite the immense distance. Magnetars form when certain massive stars collapse in supernovae, probably those with especially rapid rotation or strong initial magnetic fields. The conservation of angular momentum and magnetic flux during the collapse amplifies both quantities enormously. A typical magnetar might complete one rotation every few seconds, slower than many pulsars, but its magnetic field is hundreds of times stronger. Over time, measured in thousands or tens of thousands of years, the field decays, and the magnetar spins down, eventually becoming a quiet neutron star. Only about 24 confirmed magnetars have been discovered in our galaxy, likely because their active phase is brief on cosmic timescales. They represent an extreme laboratory for physics, testing our theories under conditions that can never be replicated on Earth. As we contemplate these extreme objects and vast distances, it's worth stepping back to consider the limits of what we can know about the universe. The observable universe, that 93 billion light-year bubble mentioned at the beginning, represents an absolute boundary on observation. We can never see beyond it because light from more distant regions hasn't had time to reach us, and with accelerating expansion, it never will. But there's no reason to think the universe stops at the edge of what we can see. In fact, if space is truly flat and infinite, as measurements suggest, then the universe extends forever beyond our horizon. There could be infinite galaxies, infinite stars, infinite planets out there, forever beyond our reach. This leads to some mind-bending implications. In an infinite universe, given enough space, every possible arrangement of matter would occur, and would occur infinitely many times. There would be infinite planets exactly like Earth, infinite copies of you reading these exact words. There would be planets almost like Earth but with small differences, and planets completely unlike Earth. Every possible configuration would exist somewhere if space is truly infinite. Of course, we can never verify this because we can only observe our finite bubble of space. These distant regions are not just observationally inaccessible but causally disconnected. Nothing that happens there can ever affect us, and nothing we do can ever affect them. They are, in a very real sense, separate universes, even though they're part of the same space. Some versions of inflation theory suggest the universe is not just vast but actually infinite, and furthermore that inflation never completely stops everywhere at once. In this eternal inflation scenario, most of space continues inflating forever, but occasionally regions drop out of inflation and form pocket universes like our own observable universe. These pocket universes would be separated by vast expanses of still inflating space. They might have different physical laws if the process of dropping out of inflation randomly determines certain properties like the strengths of fundamental forces or the masses of particles. This is speculative, well beyond what we can observe, but it emerges naturally from many inflation models. If true, it would mean our observable universe is one bubble in an infinite multiverse of causally disconnected regions, each potentially with different physics. Whether or not eternal inflation is correct, the existence of a cosmic horizon raises deep questions about what we can ultimately know. Science relies on observation, on gathering evidence about how nature behaves. But if vast regions of reality are forever beyond observation, can we ever claim to understand the universe completely? There will always be questions we can't answer empirically, even in principle. Is the universe finite or infinite? What lies beyond the cosmic horizon? Are there other universes with different physical laws? These questions might have definite answers, but those answers might be forever beyond our reach. Yet remarkably, despite these limits, we've learned an enormous amount about the cosmos over the past century. We've determined the universe's age to within 1% accuracy. We've mapped its contents, identifying dark matter and dark energy even though we don't yet know what they are. We've traced cosmic history from the first fraction of a second through 13.8 billion years of evolution. We've discovered thousands of exoplanets and begun to characterize their atmospheres. We've detected gravitational waves and observed black holes directly. We've mapped the cosmic web and determined the universe's geometry. We've watched galaxies collide and stars explode. We've seen light from when the universe was less than 5% of its current age. Human ingenuity and curiosity have carried us far, from ancient sky watchers tracking the planets to modern telescopes peering across billions of light years. Every generation has pushed further, seen deeper, understood more. The Hubble Space Telescope revolutionized our view of the cosmos when it launched in 1990, and the James Webb Space Telescope launched in 2021 is now pushing even further, observing the first galaxies that formed in cosmic dawn, studying exoplanet atmospheres in unprecedented detail, and peering through dust clouds to watch stars being born. Ground-based observatories have grown to 30-meter diameters, collecting enough light to study individual stars and distant galaxies. Arrays of radio telescopes spanning continents work together as single instruments, with effective diameters larger than Earth itself. Particle physics experiments probe the fundamental nature of matter and forces, searching for dark matter particles and testing theories about the early universe. Gravitational wave detectors grow more sensitive each year, preparing to observe collisions of supermassive black holes billions of times more massive than the Sun's. Surveys map the positions and properties of billions of galaxies, tracing out cosmic structure in exquisite detail. Cosmologists use these maps to constrain dark energy and test theories of gravity. Planetary scientists study meteorites and moon rocks, reading the chemical signatures of solar system formation. Astrobiologists investigate extreme environments on Earth, learning how life adapts and persists under conditions once thought impossible, informing the search for life elsewhere. This golden age of astronomy and cosmology shows no signs of slowing. Each new instrument, each new discovery, reveals new mysteries and raises new questions. We thought we understood the universe's composition until we discovered its mostly dark matter and dark energy. We thought galaxies evolved gradually until observations revealed they grow through violent mergers. We thought planets like Jupiter were rare until we found hot Jupiters orbiting stars throughout the galaxy. We thought neutron stars were exotic curiosities until we discovered magnetars and witnessed neutron star mergers creating heavy elements. Every answer generates new questions, and that's how science progresses. Looking forward, many fundamental questions remain unanswered. What is dark matter? What is dark energy? How do supermassive black holes form so quickly in the early universe? Is there a theory that unifies quantum mechanics and general relativity? Are we alone in the universe, or is life common? What happened in the first fraction of a second after the Big Bang? Do other universes exist? Why do the fundamental constants of nature have the values they do? These questions drive research across cosmology, particle physics, astronomy, and related fields. Some may be answered in coming decades, while others might require centuries or prove unanswerable with any conceivable technology. But perhaps the most remarkable thing about all this knowledge is not what we've learned but that we've been able to learn it at all. We're evolved apes on a small rocky planet, able to comprehend cosmic phenomena occurring billions of light years away or in the first moments after creation. We've built instruments that detect ripples in space-time itself, mapped radiation from when the universe was 380,000 years old, and calculated what will happen trillions of years in the future. We've understood that we're made of atoms forged in stellar cores, that the ground beneath our feet is riding on tectonic plates, that life arose through evolution by natural selection, that space and time are interwoven and malleable. None of this was obvious. None of it matched common intuition. All of it required centuries of careful observation, brilliant insights, and gradual refinement of our theories. The universe turns out to be stranger and more wonderful than anyone imagined. Space expands, carrying galaxies away from each other at accelerating speeds. Time runs at different rates depending on gravity and velocity. Matter can be compressed to infinite density in black holes. Particles pop in and out of existence in quantum foam. The vacuum of space isn't empty but filled with fields and dark energy. Neutron stars spin hundreds of times per second with magnetic fields that warp spacetime. The same laws of physics that govern falling apples also govern the orbits of planets, the fusion reactions in stellar cores, and the evolution of the entire cosmos across billions of years. We've learned that humans aren't the center of anything. Earth orbits an ordinary star in an ordinary galaxy in an ordinary part of the universe. There's nothing special about our location or our time. The laws of physics appear the same everywhere. Light from distant galaxies shows the same spectral lines from the same elements, undergoing the same transitions as in terrestrial laboratories. The physics we discover here applies throughout the cosmos. This universality is part of what makes science possible. We can study distant stars and galaxies because they obey the same rules as nearby objects. Yet despite our ordinary location, we can claim one achievement that may be rare in the cosmos. We've figured much of this out. We've pieced together cosmic history from fragmentary evidence. We've inferred the existence of dark matter from galactic rotation curves and gravitational lensing. We've deduced that the universe is expanding and accelerating from observations of distant supernovae. We've calculated the age of the universe from the temperature of the CMB and the abundance of light elements. We've determined that supermassive black holes lurk in galactic centers from watching stars orbit invisible points at tremendous speeds. Each of these conclusions required not just observations but theoretical frameworks to interpret them, mathematics to make precise predictions, and the scientific method to test hypotheses against evidence. The story of the universe is still being written. Every observation adds new chapters, and sometimes forces us to revise earlier sections. The discovery of dark energy rewrote our understanding of cosmic fate. The detection of gravitational waves opened entirely new chapters about black hole mergers and neutron star collisions. The discovery of thousands of exoplanets transformed planetary science from a field with 9 examples to one with thousands. Future discoveries will surely surprise us again, revealing phenomena we haven't yet imagined. That's the nature of exploration. You don't know what you'll find until you look. As our instruments improve and our understanding deepens, we're approaching questions that previous generations could only speculate about. Are we alone in the universe? Within the next few decades, we may have partial answers. We're beginning to characterize the atmospheres of rocky planets and habitable zones, searching for biosignatures. We're sending probes to ocean worlds in our own solar system like Europa and Enceladus, where liquid water beneath icy crusts might harbor life. We're scanning the sky for signals from technological civilizations. We're developing theories of how life begins and what conditions it requires. The question of our place in the cosmos, whether we're unique or common, has driven human thought for millennia, and we're finally developing the tools to answer it. The universe revealed by modern science is almost incomprehensibly vast in space and time. Light from the most distant galaxies has been traveling toward us for more than 13 billion years, spanning distances so immense that human minds can barely grasp them. That light began its journey when the universe was young, before the solar system existed, before the Milky Way had taken its current form. It has traveled across expanding space for most of cosmic history, finally arriving at Earth to be captured by telescopes and analyzed by human astronomers. When we see those distant galaxies, we're looking back through time, witnessing the universe as it was in its youth. In a very real sense, telescopes are time machines, allowing us to observe the past directly. This ability to look back in time is one of astronomy's unique advantages. Most sciences study the present, perhaps extrapolating backward or forward. Astronomers can directly observe the past by looking at distant objects. We can watch cosmic history unfold by comparing galaxies at different distances. We can see how star formation rates have changed over billions of years, how galaxies have grown through mergers, how the universe has evolved from hot dense plasma to the cold structured cosmos we inhabit today. Every photon carries information about when and where it was emitted, and sophisticated analysis can extract that information, revealing details about temperature, density, composition, and motion. The universe tells its own story to those who know how to listen. That story is one of change and evolution, from simplicity to complexity. The early universe was remarkably uniform, with matter distributed almost evenly throughout space except for tiny quantum fluctuations. Over billions of years, gravity amplified those tiny variations, pulling matter together into increasingly complex structures. First came the dark matter halos, then within those halos gas collapsed to form the first stars. Those stars fused hydrogen into helium and heavier elements, then exploded, enriching their surroundings with new elements. Subsequent generations of stars formed from enriched gas, able to form planets, and ultimately life. The universe became more structured, more interesting, more diverse over time. This evolution from simplicity to complexity occurred throughout the cosmos, driven by gravity, nuclear fusion, and the laws of physics. Earth is a product of that cosmic evolution. The hydrogen in our water formed in the Big Bang. The carbon, nitrogen, and oxygen in our bodies formed in stellar cores. Heavier elements like iron formed in supernova explosions. All of this matter has been recycling through multiple generations of stars over billions of years. The solar system condensed from a cloud of gas and dust enriched by countless previous stars. Earth formed from the collision and gradual accumulation of rocky material in the inner solar system. Life arose from complex chemistry involving those recycled elements. Humans evolved through billions of years of biological evolution. And now some humans study cosmology, tracing their origins back through time to the Big Bang itself. We are the universe becoming conscious of itself, matter organized in such a way that it can contemplate its own existence. This perspective, this cosmic view, is one of humanity's great achievements. For most of history, humans understood little about the universe beyond what they could see with their eyes. The sky was a dome of lights with unknown nature and purpose. The development of the scientific method, the invention of the telescope, the gradual accumulation of observations and theories over centuries, all of this has led to our current understanding. We now know what stars are, why they shine, how they're born and die. We know what galaxies are and how many exist. We know how old the universe is and how it began. We know the fundamental laws governing matter and energy. This knowledge is hard-won, the result of countless scientists making observations, performing experiments, developing mathematical frameworks, and testing predictions against reality. Yet for all we've learned, mystery remains. The universe still has secrets it hasn't revealed. Dark matter's identity remains unknown despite decades of searching. Dark energy's nature is a complete puzzle. We don't understand what caused inflation or what the inflaton field was. We don't know if the universe is finite or infinite, whether other universes exist, or why the laws of physics have the form they do. We don't know if we're alone in the cosmos. We don't know what happened in the first instant after the Big Bang or what, if anything, came before. These are not failings of science but opportunities for future discovery. Every answered question reveals new puzzles, and that's what keeps science vibrant and exciting. The universe is vast almost beyond imagining, far larger than humans will ever be able to explore physically. The distances between stars are so immense that no plausible propulsion technology could carry humans to even the nearest stars within a human lifetime. The distances between galaxies dwarf even interstellar distances. The observable universe contains regions we can never reach because space is expanding faster than light could carry us there. We're confined to a tiny bubble in an enormous, possibly infinite cosmos. Yet our minds are not so confined. Through mathematics, physics, and careful observation, we can understand distant galaxies, probe the properties of black holes, trace cosmic history across billions of years, and predict what will happen trillions of years in the future. The light speed limit prevents us from physically visiting distant places, but doesn't prevent us from learning about them. In contemplating the universe's vastness, its age, its contents, and its ultimate fate, we're confronted with questions about meaning and purpose. In a cosmos so vast and old, where we occupy such a tiny space for such a brief time, do our lives matter? That's a philosophical question, not a scientific one, but it's worth reflecting on. Science tells us what the universe is and how it works. It doesn't tell us what we should value or how we should live. Different people will draw different conclusions. Some find the cosmic perspective humbling or even nihilistic. Others find it inspiring, a reminder of how remarkable it is that the universe has produced thinking beings capable of understanding their own origins. Perhaps what matters is not the size of the stage but what happens on it. Perhaps consciousness and intelligence are rare and precious, making our existence significant despite our cosmic insignificance. What we can say with certainty is that we're living in a remarkable era. We're among the first generations of humans to understand the universe's basic structure and history. We've looked back to nearly the beginning of time, forward to nearly the end. We've mapped the cosmos from the smallest quantum scales to the largest cosmic structures. We've discovered planets around other stars, detected gravitational waves, and photographed black holes. Future generations will know more, will see further, will understand deeper. But they'll build on the foundation we're establishing now. The knowledge we're accumulating is humanity's shared inheritance, a treasure that grows with each new discovery. The universe is 13.8 billion years old, 93 billion light-years across in its observable extent, composed mostly of mysterious dark matter and dark energy, filled with 2 trillion galaxies each containing billions of stars, evolving according to physical laws we've largely deciphered. It began in a Big Bang, underwent exponential inflation, cooled and expanded, formed atoms and then stars and galaxies, and will continue expanding perhaps forever. Within it, at least one planet has produced life, intelligence, and civilization. That civilization has looked outward at the cosmos and inward at matter's fundamental nature, and has learned remarkable things about both. We stand at a unique moment in history, able to peer across cosmic distances and timescales, armed with powerful instruments and sophisticated theories, yet still surrounded by profound mysteries waiting to be solved. The journey from ignorance to understanding has been long and difficult. Ancient peoples watched the stars move across the sky and wove stories to explain what they saw. They noticed patterns, tracked the seasons, used the heavens for navigation and timekeeping. But they couldn't know what stars truly were or how far away they lay. The idea that we live on a planet orbiting a star, that stars are distant suns, that galaxies exist beyond our own, that the universe had a beginning and will have an end, none of this was obvious or intuitive. It took careful observation, mathematical reasoning, physical insight, and willingness to follow evidence wherever it led, even when it contradicted common sense or cherished beliefs. The Copernican revolution displaced Earth from the center of creation. Darwin's theory of evolution showed that humans arose through natural processes over immense time. Einstein's relativity revealed that space and time are not absolute but relative and malleable. Quantum mechanics demonstrated that reality at its smallest scales is probabilistic and strange. Modern cosmology has shown that we're made of atoms that are a cosmic minority, living in one galaxy among trillions, in one region of a potentially infinite universe. Each of these revelations has displaced humans further from any special position, yet paradoxically has also revealed how much we're capable of understanding. We may not be the center of anything, but we can comprehend the cosmos that produced us. The methods we've developed for studying the universe have applications far beyond astronomy. The scientific method, the idea of testing hypotheses against evidence and discarding theories that don't match observations, applies across all domains of inquiry. Statistics developed for analyzing astronomical data find use in medicine, economics, and countless other fields. Technologies created for telescopes and particle detectors have spawned new industries and medical devices. The mathematical frameworks developed for physics describe phenomena from the quantum realm to the cosmic scale. The knowledge we gain about the universe isn't just abstract. It has practical consequences and enriches our understanding of reality at every level. Consider what we've learned about matter and energy. At the most fundamental level, everything we see is made of particles like quarks and electrons, governed by four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These forces shape everything from the structure of atomic nuclei to the evolution of galaxies. The electromagnetic force binds electrons to nuclei, creating atoms and enabling chemistry and ultimately life. The strong force holds quarks together in protons and neutrons and binds those particles together in atomic nuclei. The weak force governs radioactive decay and plays a crucial role in stellar fusion. Gravity, the weakest force on small scales, dominates on cosmic scales, shaping the orbits of planets, the structure of galaxies, and the evolution of the universe itself. These forces and particles are described by the Standard Model of particle physics, one of the most successful theories in science. It makes predictions accurate to many decimal places, explaining virtually everything we observe in particle physics experiments. Yet we know it's incomplete. It doesn't include gravity. It doesn't explain dark matter. It doesn't explain why particles have the masses they do or why there are 3 generations of particles with similar properties. It doesn't explain why the universe contains more matter than antimatter. A more complete theory, perhaps something like string theory or loop quantum gravity or something not yet imagined, will eventually supersede the Standard Model, incorporating it as a special case while explaining phenomena it cannot. Similarly, Einstein's general relativity describes gravity with extraordinary precision, passing every experimental test from the precession of Mercury's orbit to the detection of gravitational waves. Yet it too must be incomplete because it predicts its own breakdown at singularities inside black holes and at the Big Bang itself. Where matter becomes infinitely dense and spacetime infinitely curved, the equations produce meaningless infinities. Most physicists believe these infinities indicate that general relativity breaks down in these extreme conditions and must be replaced by a quantum theory of gravity that remains undiscovered. Merging quantum mechanics and general relativity into a single consistent framework is one of the great unsolved problems in theoretical physics. These limitations don't diminish the achievements of the Standard Model and general relativity. Both theories are extraordinarily successful within their domains of validity, and both make predictions confirmed by countless experiments and observations. A theory doesn't need to be absolutely complete to be useful and accurate within its regime of applicability. Newtonian mechanics isn't wrong, even though it's superseded by relativity and quantum mechanics at extreme scales. It's an excellent approximation for everyday phenomena and is still used for most engineering applications. Similarly, future theories that supersede the Standard Model and general relativity will likely reduce to those theories in the conditions where we've tested them. The new theories will extend our understanding to new regimes while preserving what we've already learned. This is how science progresses, through successive approximations that get closer to truth. Each generation builds on the work of previous generations, correcting errors, extending domains of validity, and occasionally revolutionizing our conceptual frameworks. The process is never complete because there's always more to learn, always deeper questions to ask. Even when we think we understand something thoroughly, nature surprises us. Who would have predicted dark energy before observations showed cosmic acceleration? Who would have anticipated that most matter in the universe would be invisible dark matter? Who could have foreseen quantum entanglement, or the EPR paradox, or any of quantum mechanics' strange predictions before experimental evidence demanded them? Nature is under no obligation to make sense to us or to match our intuitions. Our brains evolved to survive on the African savanna, not to understand quantum mechanics or cosmology. The fact that we can understand these things at all, using mathematics and careful reasoning to extend our intuition beyond its evolved range, is remarkable. Mathematics provides a language for describing patterns and relationships that go far beyond what words can express. Physical equations capture regularities in nature and allow us to make precise predictions. When those predictions match observations to many decimal places, we gain confidence that we're capturing something real about how the universe works, even if the underlying concepts seem strange or counterintuitive. The dialogue between theory and observation drives scientific progress. Theorists develop mathematical models that make testable predictions. Observers and experimenters test those predictions. When predictions match observations, confidence in the theory grows. When they don't match, theories must be revised or abandoned. This feedback loop has proven incredibly powerful for uncovering nature's secrets. It's self-correcting because wrong ideas eventually fail empirical tests. It's progressive because each generation can build on the tested knowledge of previous generations. And it's universal because the same methods work across all scientific domains. In cosmology, this interplay between theory and observation has led to our modern understanding of cosmic history. The observation that distant galaxies are receding, with velocity proportional to distance, led to the Big Bang theory. The theory predicted the universe should have been hotter and denser in the past, which led to predictions about the abundance of light elements formed in the first few minutes. Observations confirmed those predictions remarkably well. The theory also predicted the existence of the cosmic microwave background, which was discovered accidentally and matched theoretical predictions. More detailed observations of the CMB revealed the tiny fluctuations that seeded structure formation, matching predictions from inflation theory. The discovery of accelerating expansion required adding dark energy to our models, but the resulting model fits diverse observations from supernovae to galaxy clustering to the CMB. This concordance model, also called lambda CDM for the cosmological constant lambda representing dark energy, and CDM for cold dark matter, has become the standard framework for cosmology. It's supported by multiple independent lines of evidence, and makes predictions that continue to be confirmed by new observations. Yet it also highlights our ignorance. Two of its major components, dark matter and dark energy, are mysterious. We've given them names but don't understand their nature. The model also requires inflation to explain the universe's flatness and uniformity, but the mechanism driving inflation remains uncertain. These gaps in our understanding represent frontiers for future research. As observations continue to improve, we'll test the concordance model more stringently, and may find discrepancies that point toward new physics. Already there are some tensions in the data. Different methods of measuring the Hubble constant, the rate of cosmic expansion, give slightly different results. This could be measurement error, or it could hint at new physics. Resolving this tension is a major goal of current cosmology. Similarly, the exact properties of dark energy are still being constrained. Is it truly constant, or does it vary over time or space? Different answers would point to different underlying physics and different ultimate fates for the universe. In the search for dark matter, experiments are pursuing multiple strategies. Direct detection experiments deep underground try to catch dark matter particles colliding with ordinary atoms. Indirect detection experiments look for signals from dark matter particles annihilating or decaying in regions of high dark matter density like the galactic center. Particle colliders try to produce dark matter particles in high-energy collisions. Searches look for axions, a hypothetical light particle that could constitute dark matter. So far, these searches have excluded many possibilities but haven't yet made a positive detection. The parameter space of possible dark matter properties is vast, and we may need multiple generations of increasingly sensitive experiments before finding the answer. The search for life beyond Earth similarly employs multiple approaches. Missions to Mars search for evidence of past or present microbial life in Martian rocks and soil. Missions to ocean worlds like Europa and Enceladus will search for life in subsurface oceans. Telescopes study exoplanet atmospheres looking for biosignatures. Radio telescopes scan for signals from technological civilizations. Laboratory research investigates how life can arise from chemistry and what conditions it requires. Each approach addresses different aspects of the question and provides different kinds of evidence. Finding microbial life on Mars or Europa would suggest life arises readily wherever conditions permit. Detecting biosignatures on an exoplanet would show life exists elsewhere in the galaxy. Receiving a radio signal from another civilization would answer definitively whether intelligent life is common or rare. The implications of discovering life elsewhere would be profound, affecting everything from biology to philosophy. If we find life on multiple worlds in our solar system, it would suggest life is common throughout the universe. If that life shares biochemistry with Earth life, it might indicate a common origin, perhaps via panspermia where microbes travel between planets on meteorites. If it has different biochemistry, it would show that life can arise through multiple independent pathways. If we find intelligent civilizations, it would raise questions about why they haven't colonized the galaxy or contacted us, reviving the Fermi paradox. It would also provide insights into what happens to technological civilizations over long timescales, whether they persist and flourish or tend towards self-destruction. Conversely, if we search thoroughly and find no evidence of life elsewhere, that too would be significant. It might suggest life is extraordinarily rare, perhaps requiring such an unlikely combination of circumstances that it occurs on only a tiny fraction of worlds. Or it might suggest that while simple life is common, intelligence or technology is rare. Or perhaps intelligence is common but tends not to produce detectable technological signatures, either because civilizations don't last long or because they choose not to advertise their presence. The absence of evidence isn't proof of absence, but if we search carefully across many worlds and many wavelengths and find nothing, we'd have to seriously consider that we might be alone, or at least very isolated in space and time. This possibility, that intelligence might be rare in the cosmos, makes humanity's existence even more remarkable and perhaps more precious. If we're alone, then we're the universe's only way of understanding itself, at least in our cosmic neighborhood. That would come with responsibilities to preserve our civilization, to ensure we don't destroy ourselves through war or environmental catastrophe or other self-inflicted disasters. It would make the long-term survival and flourishing of intelligent life a cosmic imperative, not just a human concern. On the other hand, if intelligence is common, then we're one instance among many, and what happens to us matters less on cosmic scales. Either way, the question of whether we're alone ranks among the most profound we can ask. As we look to the future, both near-term and distant, several trajectories seem clear. Technology will continue advancing, giving us ever more powerful tools for studying the universe. Telescopes will grow larger and more sensitive. Gravitational wave detectors will observe fainter signals from greater distances. Particle experiments will reach higher energies or greater sensitivities. Computing power will enable more detailed simulations and analysis of larger datasets. These technological advances will lead to new discoveries we can't yet anticipate, just as previous generations couldn't have predicted what we've learned. On longer timescales, humanity faces choices about its future in the cosmos. Will we remain confined to Earth, or will we spread to other worlds? Will we survive long enough to become a truly space-faring civilization? The challenges are immense. Space is hostile, radiation-filled, and vast. The nearest stars are light years away, requiring journeys of decades or centuries even at a substantial fraction of light speed. Terraforming planets to make them habitable would take centuries or millennia. Building habitats in space would require enormous resources and engineering. Yet the potential rewards are also immense. Access to resources and space beyond anything Earth can provide, survival insurance against planetary catastrophes, and fulfillment of the urge to explore that seems fundamental to human nature. Some scientists and futurists envision humanity spreading through the solar system over the coming centuries, establishing settlements on Mars, mining asteroids, building rotating habitats at Lagrange points, perhaps eventually constructing megastructures that harvest entire stars' energy output. Others focus on robotic exploration, arguing that sending machines is more practical and cost-effective than sending fragile humans who require life support. Perhaps both approaches will be pursued, with robots scouting ahead and humans following when destinations are proven viable. Or perhaps advances in biotechnology will blur the distinction, allowing us to modify ourselves for survival in hostile environments, or to upload our minds into machines that can endure conditions biological life cannot. These are long-term considerations, probably beyond the timescale of anyone alive today. More immediately, humanity faces challenges on Earth that will determine whether we have a long-term future at all. Climate change, resource depletion, and other risks threaten our civilization's continuity. Successfully navigating these challenges requires applying the same scientific thinking that has revealed the cosmos's nature, gathering evidence, testing hypotheses, updating beliefs based on data, and taking collective action based on the best available knowledge. The methods that work for understanding the universe also work for solving practical problems, if we have the wisdom to use them. In the meantime, the universe continues its ancient dance, indifferent to human concerns. Stars are born in nebulae and die in supernovae. Black holes spiral together and merge, sending gravitational waves across space. Galaxies collide and merge over hundreds of millions of years. Cosmic expansion continues, accelerating under dark energy's influence, carrying distant galaxies ever farther away. In 1 trillion years, the sky will be much emptier as expansion carries all but the nearest galaxies beyond the cosmic horizon. In 1 googol years, the last black holes will evaporate and the universe will be a cold, dark, nearly empty void. These timescales are so vast they make the current age of the universe seem like the opening moments of eternity. Yet here we are, 13.8 billion years after the beginning, living in an era when stars still shine and galaxies still fill the sky, on a planet where life has flourished and given rise to consciousness and intelligence. We've learned to read the story written in starlight, to decode the message carried by ancient photons that have traveled across cosmic distances and timescales to reach us. We've learned the language of mathematics and physics that describes how matter and energy behave. We've learned to ask questions about where we came from and where we're going, and we've developed methods for finding answers. We've become, in some sense, the universe's way of knowing itself. This knowledge is both humbling and exhilarating. Humbling because it reveals how small we are, how brief our existence, how contingent our presence on cosmic outcomes we can't control. The universe was here long before us and will continue long after we're gone. Everything we build will eventually decay. Every record will eventually be lost. On cosmic timescales, humanity's entire existence might be just a brief flicker, gone in an instant. Yet it's also exhilarating because consciousness and intelligence are rare and remarkable phenomena. The fact that matter can organize itself into patterns that think, feel, wonder, and understand is extraordinary. The fact that such patterns have arisen and persisted long enough to comprehend the cosmos is a triumph against entropy and randomness. We don't know if this triumph is temporary or if intelligence has a long-term future in the universe. We don't know if we're alone or one among many. We don't know if consciousness is an inevitable emergent property of complex systems or a cosmic accident unlikely to be repeated. We don't know if the universe has purpose or meaning beyond what we create for ourselves. These are deep questions, some philosophical rather than scientific, and different people will answer them differently based on their values and beliefs. Science can inform these questions by revealing the context in which they must be answered, but it can't answer them definitively because they involve subjective judgments about meaning and value. What science can tell us is what the universe is, how it works, where it came from, and where it's going. It can tell us about the Big Bang, cosmic expansion, galaxy formation, stellar evolution, the formation of planets, and the conditions necessary for life. It can tell us about atoms and molecules, forces and particles, space-time and gravity. It can tell us about the observable universe's extent and age, about the dark matter and dark energy that fill it, about the fate that awaits it trillions of years hence. This knowledge is hard-won, the product of centuries of observation, experimentation, and theoretical development by thousands of scientists building on each other's work. The picture that emerges is one of profound beauty and complexity. The universe operates according to elegant mathematical laws that we can discover and understand. It evolves from simple initial conditions to create intricate structures through processes we can model and predict. It contains mysteries we're working to solve and likely mysteries we haven't yet imagined. It's vast beyond human comprehension yet describable through equations we can write on a chalkboard. It's ancient beyond human experience yet young compared to its ultimate future. It contains realms of extreme physics beyond anything we can create in laboratories, natural experiments testing our theories under conditions we could never reproduce. As we've surveyed the universe from its beginning to its end, from its smallest constituents to its largest structures, certain themes recur. One is scale, the mind-boggling range of sizes and timescales in nature, from subatomic particles to cosmic voids, from quantum fluctuations to the heat-death of the universe. Another is evolution, how simple beginnings give rise to complexity through physical processes operating over time. Hydrogen and helium from the Big Bang evolved into the periodic table of elements through stellar nucleosynthesis. Those elements evolved into planets, oceans, and ultimately life through chemistry and self-organization. Life evolved through natural selection into the biosphere's magnificent diversity, including eventually beings capable of understanding their cosmic context. Another theme is unity, how seemingly disparate phenomena are connected by underlying principles. The same gravity that makes apples fall shapes the orbits of planets and the structure of galaxies. The same electromagnetism that powers lightning and magnets also enables chemistry and biology. The same quantum mechanics that governs atoms also determines how stars shine. The same spacetime that we inhabit connects to every other place and time in the universe. Everything is part of one cosmos, operating according to consistent laws we're learning to decipher. Yet another theme is mystery. For all we've learned, vast realms of ignorance remain. We don't know what most of the universe is made of. We don't understand what happened at the very beginning or what will happen at the very end. We don't know if life exists elsewhere. We don't know why the universe has the properties it does or whether it could have been different. We don't know the ultimate theory that unifies quantum mechanics and gravity. We don't know if our observable universe is all that exists, or if it's embedded in a larger multiverse. These mysteries aren't failures of science but frontiers, opportunities for future discovery. This brings us back to where we started, contemplating the observable universe's vastness and the paradox of its 93 billion light-year extent despite being only 13.8 billion years old. We've journeyed through cosmic history from the Big Bang through inflation, through the formation of atoms and stars and galaxies, through billions of years of cosmic evolution, to the present moment. We've explored the contents of the cosmos, visible and invisible, from atoms to galaxies to the dark components that dominate the universe's mass-energy budget. We've contemplated extreme objects like black holes, neutron stars, and magnetars where physics is pushed to its limits. We've discussed the search for life beyond Earth and the possibility that we might be alone. We've looked forward to the deep future, and the ultimate fate awaiting the universe. Throughout this journey, one thing becomes clear: the universe is far stranger, far more wondrous, and far more knowable than anyone could have guessed before the scientific revolution. Ancient peoples who watched the stars could never have imagined that they were seeing the past, that light takes time to travel, that the universe has a history and an age. Medieval scholars who studied nature could never have conceived of galaxies beyond our own, or black holes, or quantum mechanics. Even scientists a century ago didn't know about cosmic expansion, dark matter, or dark energy. Each generation pushes further, learning things previous generations couldn't have imagined, and presumably, future generations will learn things we can't currently imagine. Yet for all that future discoveries will bring, the fundamental wonder remains constant. The universe exists, vast and ancient and strange. We exist within it, briefly, locally, as organized patterns of matter and energy capable of contemplating the cosmos that produced us. We've learned to look outward and see not just lights in the sky but distant suns, galaxies, quasars, the cosmic microwave background. We've learned to look inward and see not just stuff but atoms, particles, quantum fields. We've learned to look backward through light years and see cosmic history directly. We've learned to look forward using mathematics and physics and predict what will happen long after we're gone. This is humanity's great achievement and great privilege. We're here, now, in an era when the universe can be studied and understood, when technology gives us unprecedented reach across space and time, when theories and observations come together to reveal nature's deep patterns. We're living in the age when humanity first comprehended its cosmic context, first understood where we came from and where we're going. Future generations will know more details, will fill in gaps, will make discoveries we haven't imagined. But they'll build on the foundation we're establishing, the basic framework of cosmic understanding we've developed over the past century. The universe is 93 billion light-years across in its observable extent, but it likely extends much further, perhaps infinitely. It's 13.8 billion years old, but it will likely continue for trillions upon trillions of years or longer. It contains 2 trillion galaxies, each with billions of stars, each star potentially hosting planets. It's mostly dark matter and dark energy, substances we're working to understand. It began in a big bang and underwent inflation and has been expanding ever since, with expansion now accelerating. It cooled from a hot dense plasma to form atoms, then stars, then planets, then life, then consciousness. It operates according to physical laws we've largely deciphered, though mysteries remain. This is the universe revealed by modern science, strange and wonderful and knowable. We're part of it, made of it, products of billions of years of cosmic evolution. We're star stuff that has learned to wonder about stars. We're the cosmos contemplating itself. And though the universe is vast and we are small, though it existed long before us and will continue long after, though there's much we don't yet know and may never know, we can still claim this. We have looked at the night sky full of ancient light and worked out what it means. We have decoded the universe's story and found our place in it. And that understanding, hard-won and continually refined, is among humanity's greatest achievements, a triumph of curiosity, intelligence, and determination to know the truth about the reality we inhabit. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.